Okay, welcome back as we talk about electrochemical conventions. So, first off, there are a lot of terms, and I'm going to do my best to link these terms together in a lot of different ways to help you hopefully get these terms to be natural for you to use. But just recognize it'll take some work, but they will become natural for you to use as you practice. So, first is oxidation. Oxidation is the process where an analyte loses electrons or becomes more positive. For example, you might have O2 minus oxidizing to oxygen gas and becoming more positive. Then there's reduction. Reduction is when an analyte gains electrons or becomes more negative. After all, electrons are negatively charged. This example could be aluminum being reduced, or an aluminum ion being reduced to aluminum metal. So you see it becomes more negative from a 3 plus state to its 0th state. And some mnemonics to help you remember that. Well, there's oil rig. So oxidation is loss and reduction is gain. And what are we losing or gaining? It's electrons. Another one that you can remember is red cat, or reduction at cathode. And that's a way to remember which electrode is which. So you have cathodes and anodes in your cell, and reductions happen at the cathode. And of course, that means that oxidations happen at the anode. These are opposite processes. Another way that you could remember anode is anode means without. So anaerobic, anemia, anonymous, all of these things have an in them, and just like that, anode means without electrons is a way that you could think of it. So specifically, it means without high energy electrons. And this deficiency in electrons causes your analytes to donate electrons to that anode, because your analyte has relatively higher energy electrons. So just a note here, I've made all of these numbers whole numbers. So that's why you kind of have these larger numbers. That's why 12 electrons are being passed here. Of course, 12 electrons in actuality don't pass all at once, but this would be a multi-step mechanism that leads overall to the production of 12 electrons. And you'll see these 12 electrons, they jump from your analytes into your anode, then through your power supply, and then back through your cathode into another analyte to balance things out. And you'll notice that while electrons are moving in this direction, your current definition is actually moving in the opposite direction. So another way that you could remember what's happening at the cathode is with an X-ray source. So X-ray sources, what we do is we heat the cathodes, which then emit an electron beam that travels to the anode. Once it strikes the anode, then X-rays are emitted. Well, here, if you look at the electrochemical cell, the cathode is expelling electrons into the solution, just like an X-ray source. So half-cell reactions. Well, half-cell reactions are how we take redox couples and describe what's happening at a single electron. So here we have, this is aluminum oxide that we've melted, and it dissociates upon melting into aluminum 3 plus and O2 minus. And then we have two half-cell reactions. We have a reduction of aluminum 3 plus to aluminum metal, and that happens, of course, at the cathode. And then we have an oxidation at the anode, and that's when we go from our O2 minus to our oxygen. You'll notice it's written out here in terms of a reduction, and that's just standard practice. They're called standard reduction tables often, and we write all of these reactions as reductions. Once again, the 12 electrons are here because otherwise we might have a half a molecule of oxygen, and there's no such thing as half of a molecule of oxygen. So instead we say that there are 3, and we just balance these out with all whole numbers. So how do we go from these half cell reactions to our overall reaction? Well, how we do is we take the reduced reaction minus the oxidized reaction. And so here I've written the reduced reaction, and then we subtract off the oxidized reaction. And when we do that, one way you can do it is by flipping that reaction around, which gives you aluminum 3 plus and O2 minus, which is a dissociated form of alumina. And then we also have our oxygens here and our alumina as a product of the reaction. And you'll notice here that the electrons cancel out. So everything's balanced because we've been able to cancel out the electrons successfully. Okay, another thing for us to remember is the difference between 2 electrode and 3 electrode cells. So 2 electrode cells, they're typically used in industrial applications, and you have an anode and a cathode in those applications. For research applications where we're trying to figure out what's going on at the electrodes, we usually use a working electrode. Now, the working electrode, this is our focus. This is where we measure the current going through the working electrode as well as the potential or the voltage of that electrode. And how we do that is we have a counter electrode, and between the counter electrode and the working electrode, that's where the current is flowing, right here through our power supply. And then, so that is where we get our current measurement and our current path. We also have a reference, and no current is flowing through our reference electrode. And we measure the voltage between our reference and our working electrode here. Whereas with the 2 electrode cell, you're measuring the voltage between the anode and cathode, as well as the current going between the 2 of them. And just the important thing with your reference is that you're just keeping it at a stable potential by having a stable state of analytes in your reference electrode. So when you're measuring your working electrode voltage, you're measuring it versus a reference state, because potential is a thermodynamic concept, and we often have to use reference states for thermodynamics. The next thing we need to talk about is which way is up in our graphs. So these are voltammograms. They're very common graphs in electrochemistry, where you have potential on this axis and current on this axis. In the IUPAC convention, we have negative potentials on the left and positive at the right. And you'll notice that as we go to more negative potentials, that's when reductions occur. And when we go to positive potentials, that's when oxidations occur. Well, in the Texas convention, we flip this axis so that positive is to the left and negative is to the right. But it's still the case that when you go negative, you get reductions, and when you go positive, you get oxidations. So that's the way to tell which convention things are written in. You'll notice that they have completely different definitions of current direction. Okay, so here's my question for you that I want you to analyze before you go on to the next video. I want you to think about what half-cell reactions would occur in molten sodium chloride electrolysis. And remember that sodium chloride, upon melting, will dissociate into sodium ions and chloride ions. So that's the first question, which half-cell reactions are going to occur. And the second question is, which reaction is going to occur at the anode? So I'll give you a little bit of time. Go ahead and pause the video and work on that. And then in a few seconds, I'll give the correct answers. Okay, welcome back. So the correct answers for this. So we have sodium plus and chlorine minus. Here are the 2 reactions going on. They're sodium, of course, it only has a +1 state and a metal state that are stable. And so that's what we have going on here. And same with chlorine. So the stable phases for the chloride ion would be chlorine, the chloride minus ion, and chlorine gas. And then we say, well, which one's going to happen at the anode? And well, we know, one of our reactants needs to be chloride or sodium ions. And so anode, that means oxidation. And so which one of these reactions is the oxidation reaction in its natural state with a chloride ion as a reactant? It's of course this one. So 2 chloride ions are going to react and create chlorine gas. Okay, well, we hope you will join us for our next video on electrode potential.